Continue our conversation about kinetics. When we last met, we learned about average rate. We also learned how to measure graphically the instantaneous rate and how to express rate stoichiometrically as a condition based upon disappearance of reactant or appearance of product. So in a previous problem, we had determined that there was a rate law of the conversion of ammonium and nitrite ion into nitrogen and to water. And both of these reactants, ammonium and nitrite, were considered to be first order because if you doubled one concentration and held the other constant, you saw that the rate double. So if they're both first order, then the reaction overall is second order as you sum up the orders. So when you have a problem like you see here, and you're asked to determine the rate law, the rate constant, and the rate of the reaction given specific concentrations, do the usual. Find some trials where you have concentration staying constant, and notice immediately that doubling the concentration of reactant B has no impact on rate. Therefore, it must be zero order with respect to B. Trials 1 and 3 hold B constant, and you can see that the doubling of reactant A from trial 1 to trial 3 results in 16 times 10 to the minus 5. The factor went up by 4 times. So you can think of that as being two, let's see if I said that right. So if I'm doubling it and it goes up by 4 times, that's 2 squared or 4 times the rate. So now that we have our plan, what we can do is we can figure out our first rate law. It turns out that our rate is only dependent upon the concentration of A, zero order with respect to B, and so our rate law is simply K times A squared. So now we have our rate law. Let me make sure I make that very clear. When you double A and you see the rate increase by fourfold, then that would be, in a formula term, it would be 2 squared or 4 times the rate. So now that we have a rate law, and by the way, I'm not going to do this one right now. There's a more formal way where you can compare the rates of one trial to the rate of another and mathematically predict what the rate law is. But I'll let you read that one on your own. And what I'd like to do next then is show you how you can determine the K. So if the rate is equal to K times A concentration of A squared, you can resolve your equation to solve for K and pick the rate from a trial, in this case experiment 1. You have your concentration from experiment 1, and notice these interesting units. That's per molarity per second is how you read that, m to the negative 1, s to the negative 1. Once you have a rate law and you've got a rate constant, now you can pick the concentration from any trial, and you can solve for, let's see, I think the last thing they wanted you to do was they wanted you to fill in what the concentration might be. Let's go back and check that real quick. The third question was, now that we know the rate constant and the orders, you can use the rate law with given concentrations. And that was, yes, here we are up here. The concentration of A was 0.05. And we really don't care what the concentration of B was because it's zero order with respect to B. So all you need to do is to take that rate law and substitute in for reactant A concentration that was given. And that was the amount right here. Here is our rate constant, and you need to be very careful in these problems to make sure that you do the appropriate canceling. So for example, if that's molarity squared and you have a molarity in the denominator, you will end up with one of those molarity values canceling and leaving one in the numerator. And that s to the negative 1 meant that that second or per second was already in the denominator, so that's how this rate comes out to molarity per second. And all I've done is taken the rate constant that you calculated in part B, multiplied it by the given concentration in the question C, 0.05 molar, and now you can calculate the rate. Okay, so that's a sample exercise where given data, you can determine a rate law. You can pick data from any trial and plug that in to solve for the rate constant. And finally, given a rate constant and a rate law, you can put in any concentration to determine what the rate would be. And in real world, that's an actual practical application. What I would like you to do now, in a separate sheet of paper, which I will have you turn in to me when I see you next, is to consider the data that you see in this practice exercise. And you're going to do the same thing, determine the rate law based upon the data that you see, calculate the rate constant, and substitute in on part C some given concentrations for the two reactants to calculate the rate at those concentrations. Notice that the answers are given. I would like you to demonstrate your work or logic that proves that you came to the same conclusions that they did here at the end of sample exercise 14.6. Now, having done that, we also learned last time we spoke that you can take the integration of these rate laws and take the concentration of a reactant at time equals 0, or what we call initial concentration, and express it as the natural log. You can also do the concentration of reactant A at a specified time, and with some calculus first and then some algebra second, you can create an equation that shows a linear line, y equals mx plus b. This is a rerun, and the way that you interpret this is if you come up with either a straight line with a negative slope or a rate law that could be expressed in this format, then what you have is a first order reaction. So we use the example of methyl isonitrile turning to acetonitrile, and when you compare the data on a time versus pressure, in gases you can use pressure as the concentration measurement, you get a curvy line because the rate is changing over time. But when you take the pressure as the natural log, then you get the straight line with a negative slope. And what you need to remember is that this process is always the picture for a first order reaction. And if you take the negative of the slope, you will have the rate constant. So sometimes you have to do things graphically. So when you are using this integrated first order rate law, it can be used in something as complex as the decomposition of a certain insecticide. So another real world application. It's a first order kinetics. It has a rate constant of 1.45 per year at 12 degrees Celsius. So they're saying that's how much it would decompose as long as you use a temperature that's sort of an average temp for a time period. So the only thing that we know is that on June 1st, we start off with a concentration of 5 times 10 to the negative 7 grams per cubic centimeter. And they want to know how much would be there a year later. And the second question would be, how long would it take possibly for it to decrease to 3 times 10 to the minus 7, 3 times 10 to the minus 7 grams per cubic centimeter. So if you write down what you know, they gave us the rate constant. That was kind of them. Somebody else determined that experimentally in another real trial. And we have an initial concentration, and it looks to me like they have a final concentration too. Or excuse me, they want you to find the final concentration in the first question. So we have our time period, 1 year, and we know that the initial concentration is 5 times 10 to the minus 7 grams per cubic centimeter. So what you need to do is plug it into the equation that we learned. So you take the natural log of the insecticide at your specified time, 1 year. That would be equal to the negative of the rate constant, that's the slope. Here is my duration of time, there's the time, 1 year, and here is the natural log of the initial concentration. So you'll get when you're done solving, the natural log of the concentration at the time frame that you were looking for, but you then have to take that number and de-logify it, take the anti-log of that, which would be e to the negative 15.96, and that value that you get will be expressed in the same units of concentration, grams per cubic centimeter. So it's kind of a cool thing because they take this esoteric sort of kinetics reaction, turn it into a useful equation. Now the second question is asking not for concentration, but for a time. how long would it take for the concentration of the insecticide to decrease to a certain amount? This time what we know is the final concentration. The natural log of what we're going to finally end up with should be equal to the rate constant times this time an unknown amount of time plus the natural log of the initial concentration. This time when you solve and complete your answer, you'll get an answer in years. And if you look carefully at this, I think here it becomes year to the -1. And then since it's in the denominator of this value here, that becomes just years. So again, you can use these in very useful contexts. Oh, that's interesting formatting. Okay, let's take a look at second order processes. So if it's second order with respect to a particular reactant, you can get still a line, but this time it's the inverse of the concentration of your reactant at a specified time. And over here we'll have the inverse of the concentration of the reactant at time equals 0, or what we call initial concentration. And this time it's just KT, it's not a negative K. Let's take a look at that line. So it should give us a straight line again. The slope of the line is going to be K. And the picture that you get, let's say if we take this decomposition of nitrogen dioxide, and you've got a particular time and a particular concentration, if you plot it as the natural log, so you could create a chart where they give you time and concentrations. If you make a column that just says natural log of the nitrogen dioxide concentration, that's what these values here are. And when you graph those with time on the horizontal and the natural log of the concentration of the initial nitrogen dioxide, you get a curvy line. Not terribly helpful, because had it been first order, it should have been a straight line, and it's not. So since it's not a straight line, now what you're going to try is the inverse of the concentration of the nitrogen dioxide. So now we have the same data, a time and a concentration, but now the column that you make is the inverse of the concentration. And this time you get a plot that's a straight line with a positive slope. And that's what second order mechanisms or reactions look like. So natural log giving you a slope with negative straight line first order, but 1 over the concentration of the nitrogen dioxide or reactant with a positive slope straight line, that's an indication that it's second order. So even though data might look incomplete, you can graphically determine if reactions are first or second order. I will pick up the concept of half-life at the next Vodcast. Remember, you have a number of sample exercises to copy into your notes, including the one that I asked you to complete to show the work, proving the sample exercise at the end of, I think it was 14.7, but I could be wrong. Until next time.